Right, good afternoon. My name is Mathias Verraes from Belgium.
And my name is Gien Verschatse, also from Belgium.
And we work for a small international consultancy called Artling. We help organizations deal with complex environments through strategy, architecture, modeling, that sort of thing. For companies ranging from scale-ups to Fortune 500s and banks, Shopify and Spotify are probably our most well-known customers. Oh, and here Danske Bank for a while. Have you worked on a system that's hard to understand? It's a rhetorical question because probably yes. And very often you'll hear, oh, but it's too much abstraction or it's not enough abstraction. Right? It's always something. Right? The real problem is, of course, that it can be both, right? It can be a lack of abstraction, too much detail, not enough organization. There's no sort of structure in the code. You get these huge blocks that seem to do a lot of things, but it's not very clear what they do. Of course, it's a lot harder. It's maybe easy to write. It's always easier to add something to that, but it becomes very hard to understand the system and to read the system, which, as you may know, most of our time spent developing is spent on reading and understanding and mentally reverse engineering code very often. So it's very costly, actually. And the opposite, of course, as well, is that if we want good abstraction, it does work. It can help us. It isolates the problem from other problems, right? That's one way to think about abstraction. We tend to look at it as, oh, but in the real world, we have these things, and these are actually a super type of that thing. That's not how you should approach these problems. It's about, can I isolate one problem and solve it locally, and then I don't have to think about it anymore when I'm looking at a higher abstraction level. And where we also get it wrong is that our abstraction should actually evolve along with the problems, right? If one thing is true in software is that it's always changing. They say a software system is done when the last server has been turned off and the system is forgotten about. So as the problem evolves, as the market changes, as the competition changes, as we do new features or try new business areas, our abstraction should evolve along with that, which is also something that we don't do enough. Is anybody here into domain-driven design? A little bit, or have heard of it? Okay, so you might have heard of this concept, bounded context. Bounded context is a set of domain concepts, right? It's a model, it's a domain model. It usually has its own language, its own logic, its own abstractions. It's not necessarily a separate system. It can be, right? Ideally, you would put that in a separate service or application or whatever. But it's more about the language, the model, the logic, and the set of abstractions. And they should form, ideally, you try to find these bounded contexts, make them a coherent whole, so that they only need to understand, or as a reader, you only need to understand about that context without having to understand everything else. And it's a deliberately bounded thing, by which I mean you don't accidentally end up with good bounded context. Right? It's usually a very deliberate design choice by the designers, which is developers, but also other people involved in the design. So this is sort of a framing and an approximation to help you build an intuition for it. I treat them as understandability boundaries. Right? Are there aspects of this problem that I can understand in isolation without having to understand much of other problems? Right? That's a very good way, and that's a lot of what we do at Artling as well, helping companies with this. It's a very good way to make systems that are understandable, that are therefore more readable and evolvable and maintainable, and where you can make them work for the business as opposed to against it. Right? So find the things that belong together. Maybe you're used to this idea, which is sort of growing in software, right? That your domain model should be an isolated core in your application or in your code, right? Where it's hexagonal architecture does this. There's more, philosophies and ideas in software design that have the same notion. So the logic, everything that belongs to the problem domain you're solving is isolated, and then the rest of the code is built around it. Right? The integration, the dealing with infrastructural things, networking, databases, all these sort of things. So when we're talking about bounded context, we're talking about this sort of conceptual layer, right? That talks about the concepts and doesn't talk about the tech and the infrastructure aspects. Many people, even in domain-driven design, in that community and in that world, don't really see this difference very clearly. So I want to mention this. A domain is the area of the business, right? It's the set of activities and knowledge that they operate in, which could be, you know, logistics or finance or whatever. And then you have subdomains, of course, which are a way that the business perceives all the different aspects of doing that activity. A bounded context is separate from that. Bounded context is what we do as designers or as engineers, is organizing this knowledge and organizing these models and finding ways to build a software system architecture that allows or that creates this isolation, this sort of conceptual isolation. I know I'm talking very abstract. I will try to make it clearer with an example. So we're going to have two examples. The first one is about bounded context. The other one is a bit more about abstraction in general. This one is a bit premature abstraction. The other one is wrong abstractions. And we're going to use a warehouse. This is based on a real warehouse management system that I've consulted for. And the original idea or the organization of the code, right, is we're going to mimic how the warehouse works in how our software works, right? Which is not necessarily a bad idea, but well, you'll see what happens next. So how does a warehouse work? Trucks come in, we have to unload stuff and check off things of a manifest, etc. And then we need to take all these goods and go put them in the right place in the warehouse. So that's put away, put them on shelves and whatever. And then at some point orders come in and we have to go order pick those items, package them up and send them off on trucks again. Right? And so they conceived it the same way, right? The stuff comes in, we do all the work we need to do, and then we hand it over to put away, and that, well, department, whatever you want to call it, or group of people doing that work are going to do it. And the software system mimics that, right? So all the logic is in one of these three areas, and then there's sort of a handover, there's messages basically. Well, in reality, it was a shared database, but but it already starts breaking down when we start looking at it in a little bit more detail, right? So what I'm trying to show here with the colors are concepts, right? Does this system know anything about this concept, right? Does it have logic and language inside the code that refers to these concepts, right? Does it need to, and the lines mean, does it need to know about something else? So when we put stuff away, we need to know where to put it and remember where we put it. And then, of course, when we need to take it out again, we need to know where it is and we need to find it and go fetch it. So the concept of location is already spread across two different systems here, right? And they have to communicate about that. And then what happens is the way a real warehouse works, we drew these three boxes. But they have expedites. Expedites are when, for whatever reason, the customer needs it or pays extra for it or whatever. They need some goods to be shipped much faster, right? And they will take shortcuts. They will get priority over other orders. Now, what happens is when they know that something is coming in on a truck, and they know that they will have to send it out right away, because it's part of, there's goods on that truck that are part of the order that is expedited, they will not take all those goods, put them in the warehouse somewhere, take them out again right away and ship them. That's a lot of wasted effort, right? It's very inefficient. So obviously what they're going to do is to start just keeping those things separate at the docks, and then immediately package them in the next thing and ship them off again. So it's saving a lot of time, but in order to do that, you need to know about it, right? You need to know when you're doing inbound. Oh wait, there's stuff here that needs to be shipped right away that we shouldn't go put all the way in the back of the warehouse and go fetch it again, which is a waste of time. So there's these concepts are already here. It starts, of course, a lot of these things here that you'll see start with, especially this sort of optimizations, right? They start very locally. Somebody says, oh, wait a minute, I heard from sales that this order was expedited and that's still coming in. Maybe we should just put it here, right, and not bring it to the warehouse. So it starts with these very local, people on the floor doing, warehouse managers basically doing this sort of optimizations, and then asking for developers to add features for it, right? And to automate part of it. So, and this doesn't come necessarily in a planned way, right? It's just little bits of features that get added in different places. And then, of course, more and more stuff gets connected, right? Because to know about expedite, you need to know about orders. And of course, orders, you need to know about them everywhere. So now the concept of orders is sort of spread across all of these, right? And probably more than what I'm showing here. Sales, of course, needs to know about orders, shipping, etc. So there's more subdomains here actually that will touch on orders and that will know stuff about them. So more of the logic gets spread out over the system, right? And then it gets more complex, of course. Quality control. So customers complain that the quality of certain things is not good, right? Whatever. Specifically, the example comes from a warehouse where they did textile distribution. So these are huge 10-meter rolls of textile, and to do quality control on them, you have to unroll them, look at the textile, look at imperfections or miscolorings or any of those defects. And that is work that takes some time, of course. You have to unroll it, you have to roll it back up, you have to move it to the inspection area, you have to move it back up. So they try to make that efficient. How do you make that efficient? Well, they can't do it on everything that comes in. That would be too much. So as a rule, maybe they do it on, I don't know, 10%, 30%, I don't know, but some number of incoming goods at inbound, right? But they also have clients that are, maybe they complain a bit more, or maybe they had some bad luck, or maybe they have ordered from a vendor that isn't very reliable. So customer support asks us, or sales maybe asks us, to also do quality control specifically on certain orders, right, that need to go out. And then, so of course we now need to know about quality control in two places, and we need to know about the orders in order to know which stuff we should do more quality control on. So either the vendors that we get more complaints for, or the customers that complain more often. So again, it starts with lots of local optimizations. It's not that easy as well, because we don't just have a dedicated quality control department. What we have is people in the warehouse. Most of them were hired there because of their ability to lift these 10-meter textile rolls, not necessarily for other qualities. But some of them, they've been there for many years, they get their experience, they have seen so much textile that they actually become quite proficient in looking at the textile and spotting issues. So what we want to do is get those people to quality control when we need them, right? So maybe somebody is working on outbound, but we need some quality control done on inbound. Again, it starts with these local optimization. Right? The warehouse managers talk to each other and say, hey, can you spare this person because we need to do some extra quality control? Yeah, but we have like an expedite happening and we can't really spare them right now. Can it wait? That sort of negotiation. But over time, they try to build features, right? So now we need to know which staff is working on what, where at any given time in order to decide if we can take them away to do something else. And it becomes a sort of prioritization, optimization sort of thing, right? We need to know, not everybody can do this, but this person can do it, but they're working on that. Can we borrow them? If you program this sort of stuff badly, which sort of happens, is that people get sort of called away in the middle of one thing, and then suddenly it says, oh, you have to do that thing first, and then they're called back, and it becomes a mess, of course. And of course, and then people ignore what the computer says, and do their own optimization again. But they're all doing very local optimization. They don't see the whole. They don't necessarily have all the information, which is usually why we build software systems for that. But the software system now becomes at a point where nobody really understands it anymore, because there's all these bits of logic spread across these 3 different systems, and you sort of have to go dig in 3 systems to understand why something is happening or not happening. Of course, staff then touches on everything. I already mentioned they are needed for expedites. They are like if there's an expedite, we might put more people on it. If they need for quality control. We also start doing things like lowering the amount of quality control on inbound when we have an expedite, but it's all very, very, very messy. There's even more, right? Not everything is on. I have another picture that is a lot more messy. This is not even a mess. I call this a clean picture, right? But customer support is typically one of those areas that sort of is like an octopus, right? It has to reach into everything. Same with forecasting, right? If they want to start figuring out, what's going to happen, where should we, not just for what people will buy and what they will stock, etc., but also how much people will we need on a given day to meet our targets. So this entire mess, everything starts depending on each other a lot. And there's a lot more than what I showed. So the expedite and staff specifically here in our example, they touch on many domains. They're sort of needed everywhere. Lots of local optimizations, as I mentioned. There's another way to look at this, right? There's another way to start thinking about the system, right? Bounded context, right? So if we look at the problems we're solving, instead of the domains, right? If you ignore the top for a bit, we had this sort of naive interpretation of we'll just follow the structure of the domain, the way a warehouse works, and we'll copy that, and it didn't work. Because what a warehouse really does is not just shifting stuff, it's trying to shift stuff through the warehouse efficiently. That's the difference in making a profit and going bust, right? So the other way of looking at it that I propose here and that we worked on with the client is, what if we treat efficiency as its own bounded context? So all the logic, all the domain model, the language of efficiency is all now isolated in one area. I'm not saying it has to be a separate service. It can be, ideally maybe it is, but it's an area in the code that only talks about efficiency. It doesn't even have to know anything about a warehouse specifically. It understands things like expedites and staff. So basically it understands resources, right? It's a sort of generic-ish resource management that understands some concepts like this has priority and this has no priority. And this person can be assigned to things and this person cannot be assigned to those things. And we need to maximize the usage of these people and resources. So it's a different way of thinking, right? It's not just that we isolate some code, we isolate all those concepts, and then all the other areas of the code that need staff or that want to do expedites or whatever, they have to request availability, right? They become clients now of the efficiency thing. So we're basically turning the whole system inside out, right? We're taking the thing that was actually more important, that was sort of hidden, we sort of pull that out, lift that up into its own thing, and we actually put it in charge. It's the only thing that now decides where staff is allowed to go or where they should go. Things have to request, hey, can I get priority on this? Well, no, because this other thing has a higher priority. Maybe it's an expedite plus and they paid more or something. So they have to request availability all the time. It's centrally managed, and we can now do actual global efficiency, right? We can look at the entirety of the warehouse instead of these lots of local attempts at making something faster, which is very hard to decide if you have only very, very local knowledge. So well, one way of thinking about that system is that it was theory of constraints as a service. If you read the goal or know anything about theory of constraints, which is about how you deal with bottlenecks and flows of things or information through a system. And the system can now compare the urgency of the request. So it's a different way of thinking about the purpose of the system, and the structure came second, right? It's not copying reality, in the sense of here are the departments, or here are the business domains, or here are the the teams that we have in our organization that we each build a thing for. But it's what are we really trying to solve? What are the hardest problems in our business? Can we isolate those problems, build for that specifically, and then maybe find structure that that works for it? We could do the same thing with other things, right? I used locations in the beginning. That could be something that is centrally managed, and all the different areas of the system need to request where something is, or where to put something, and it's centrally managed. You'll find that the more you extract all of these things, that the original things, of course, become much smaller and much simpler. Maybe they would even disappear over time. I don't know. But it's a different way of looking than the superficial domain boundaries. And this new model, right? These new locations bounded context, this new efficiency bounded context, they are internally consistent. They have their own set of rules. They don't have to, get permission from another system or anything. They have their own rules and logic and everything. It's sort of a black box for the other systems. That should be clear by now, I think. So it's self-contained, it's decoupled. And the more you do that, everything else also becomes easier and more understandable. It's like a game of Mikado, where the more you pull out, the easier it becomes to deal with the mess that remains. So once again, bounded context as a consistent model, a language, an explicit boundary, right? We chose to draw that box, right? And we deliberately make sure that we keep it clean and only things relevant to efficiency are in there, and that other things don't have any knowledge about the insides of that black box. So it's a boundary of language, meaning, right? Co-understandability. I can understand this thing in isolation. So somebody working on efficiency wouldn't have to understand everything about the other systems anymore, and vice versa, right? So you get small areas of understandability. Somebody new joining the company, a new engineer, wouldn't have to learn everything to be productive. They could become productive very fast in one of those contexts, which is a huge advantage, right? I already mentioned that. So this is one example where it's sort of at large scale, pulling out entire responsibilities, but looking at them really from, finding the right angle of looking at them that works for the business. I'll now give the mic to Gien, who will talk about something entirely different, a real complex domain.
Yes, forget everything you just learned about warehouses. We're going into research and development in the biotech industry. And what you have in the research and development is a lot of workflows. They're sort of your domains that you have there. And a single workflow knows how to do one thing, but it knows how to do that one thing very well. And it also wants to improve doing that one thing very well. And I know that makes no sense to you right now, so I have an example. So this is a workflow. It's a very simple one. In the company I worked for, we had about 12. They were a lot more difficult than this. So basically, we have 6 steps in the workflow. We upload a file which actually contains the DNA, because we're in the biology. We actually select which DNA we would like to build. That's the second step. And then we prepare the plates. And plates are just plastic things with holes in them. And those holes are called wells. Right? So you have a plate and a well, and you have source plates. And if you want to build DNA, you need a destination plate. And you also need to know how to combine the source plates so that you actually get to the destination plate. And you do that with a script on a liquid handler, and then you wait. So when it says transform and wait for plate reaction, it just means you put it in a tiny sort of temperature safe environment, and then you wait while nature does its thing and actually creates new DNA for you. And then you verify that it actually succeeded. So this is a very simple workflow of what happened when you're doing research and development in a bio industry. And of course, we had one of the most awesome models ever to do this, which is a single bounded context. It was a monolith with a single abstraction called workflow. I call it the one to rule them all syndrome. Has anyone sort of worked in a system where you had the one to rule them all? Oh, I see a few hands. It's horrible, isn't it? Yeah. There is just no understandability there at all, which makes sense because you have 10 of these very complex workflows in the lab, and then if you sort of want to change something about that one workflow, all you have is this one thing that does everything. So there's very low understandability. There's very high complexity because you have to create exceptions all the time. Your code is just full of if statements. Oh, if it's actually this workflow, please don't do this, or skip this step, or pick another step. You cannot test this properly because it has to do so much. So you have a lot of bugs. The thing is basically on fire every day. You have users coming to you saying, hey, I would like to try to do this, but the thing just blows up. Fun fact, the company was situated in San Francisco. We were all in Europe. So that meant that mostly at 10 or 11 p.m., those things started to blow up because that's when they were trying to use it. Fun times. And how did we get there? So Mathias talked about you can't just look at your domain boundaries, but as a software developer, we sometimes have this habit of just looking at something technical and only technical. And it's like, well, a workflow is a workflow, and I can make the perfect abstraction over all of it. I'm pretty sure it's going to work. And they first tried to do that for 4 workflows. And that didn't work, and the thing was on fire all the time. And then they said, you know what? We just haven't found the right abstraction yet. Let's try it for even more workflows this time, which also didn't work because the person who created the abstraction just could not explain to any of the other software developers anymore how it worked. There were a lot of metaphors which nobody understood. And I worked for the DNA building pipeline or workflow, and I could not see how that worked and how it was in there. But yes, so what we have to do is that we sort of have to go back to the beginning, to how can we actually get understandability back into this system. So I'm going to pick 2 workflows here because they were my specialty, which is building DNA, which is just building small pieces of DNA, and we call that DNA building. And what happens is you build even smaller pieces, and then you put that in the oven again, and then it combines, and then you get a small piece of DNA, and then you take a very long piece of DNA, and you look at it, and the picture sort of shows it, so you say, well, you get out, you get in. And that is strain building, and that's all there is to it. It's like a lot of cutting and replacing things. I'm going to look at those. Now, what they have in common is that you have to do a lot of liquid transfers. You sort of have to pick something from one plate. So that's actually a picture of the plate and the wells I talked to you about, the little holes in there. And you have to sort of pick it up, and you have to put it on another plate, right? We have the source plates and we have our destination plates, and we have to do that. And you also want to evaluate whether or not something was successful. We want to know we actually created that piece of DNA correctly, because nature is not always willing to do what it has to do. So sometimes it fails for no good reason, even if there are no bugs in your software. So you want to test whether or not it was successful. And they have that in common. So let's look at the liquid transfers. So this is a stamp. It's what we call a stamp. And what it is that, well, you take a tiny bit, so we're talking nanoliters here, like very, very small amounts. And you take a bit from all your source plate, and you just put it exactly where it was in your destination plate. So whatever liquid is in A1, you put it in A1 on your destination, right? So you sort of stamp a copy on the destination plate. A bit more complicated is the dilution. And that means that you actually do two stamps. So you take a bit from plate A, and you put it exactly in your destination plate, and then you take a bit of plate B, and you put it in that single destination plate again, giving you a different sort of liquid inside, because they're now combined there. But it's still just two stamps that you have to perform. And then even a bit more difficult, it's called a compression. And that is that, so you have 4 source plates, which is very unhandy to carry around in a lab. So you would like to go back to a single plate. So you take a bigger plate, and you just put the liquids of all those 4 plates in a very specific pattern on your destination plate. And then you have a single plate again, which just contains all the liquids of the first 4 plates. You're with me? Great. But people hear biology and how complex it is, and they're always like, oh no, I will not understand it, but it's actually pretty easy. It's cut and paste and move a lot of liquids around. That summarizes biology.
Anyone could do it.
Anyone could do. When I started working there, I knew absolutely nothing about biology, so I had to learn it from scratch, and I was able to, and I actually delivered quite useful software. So all of you can very much go work in biology as well as a software developer. That's the good news of this talk. So if we look at the domains we had, I said we had DNA building, that was a workflow, and I had strain building, and that was a workflow. And they both have liquid transfers. Now, liquid transfers is something that I can make a good model for. I can abstract the complexity of these liquid patterns that I have to program, and I can put that behind a different boundary. So that if I want to understand how DNA building works, I can actually focus on the high-level steps it has to do, and I don't have to understand what a compression is, and I don't have to understand what a stamp is. I just have to talk to liquid transfers in order to actually do that. So as a designer or as a software developer, you do need to understand the domain well enough to know what you can add to your abstraction and what kind of domain logic you just have to leave out. Because there is something called a hitpick. And a hitpick, from a programming perspective, well, you know, a stamp and dilution and a compression, I could program that it's an algorithm, and I programmed that and it worked. But from a programming perspective, it's just random. Like, it does not make any sense. But if I look from a domain perspective, it makes a lot of sense because I want to build that small piece of DNA. And I do that by building even smaller pieces of DNA. So then what I need in my destination plate are all the 5 pieces that's going to make up that small piece of DNA, and I need to put that in A1. And I need to go search on my plates where exactly are the pieces that I need. And I need to take a little bit of liquid from all of them, and I need to put them in A1. That's how you actually create DNA. And then you wait for 3 days. So I need to know here what is inside these plates. And up until this point, with my other examples, I didn't care what was inside because I had a nice little pattern and I could program it. So I don't put hitpick in this boundary because for a hitpick, I need to know what is inside. For everything else, I don't. And it was just, you know, would be so much more information I would have to give this interface if I would add a hitpick to it as well. So I leave it out. I keep it in DNA building and I keep it in strain building, where I actually know what is inside all of these wells. Right? So when you're thinking about created bounded context, you sort of need to think, we separate, you know, on something that we need to know and what we actually can afford not to know. And then we also need to know the exceptions to that rule. And that's sort of how you can find nice boundaries in your own system with this little technique. And of course, we have liquid transfers, and we don't do that manually because takes a lot of patience and precision. They did used to do that manually, but now we have robots. This is actually a very small robot. The robots we actually have to walk around them. So they were quite enormous things. And they have needles, and you put in the source plates, and you put in an empty destination plate. And robots know how to do, either they're very generic but a bit slow, or they're very specific. We had a robot that just knew how to do well compression. That was all it knew how to do, but it could do it so fast. So that sort of different robots do different things. Most of the time, they actually are assigned to a specific workflow, and a workflow is most of the time an entire department, because it's not the 6 steps that I showed you. It's more of the 38 steps that it has to perform. So they have their own robots in order to not be bothered, in order to not do that efficiency bounded context that you need to. So we don't need that here because we just get our own robots. And we do need to give them instructions, because right now they are not supported by artificial intelligence yet. So you need to give them work lists, right? So we plan the liquid transfers in that bounded context. We give that back, and then the workflow says, okay, please robots, execute this now. But talking to a robot and giving it that work list is also a lot of technical knowledge that goes behind it. So I didn't want to leave it in there either. I don't need to know how robots work in order to understand how my workflow works. So pull that out into a separate bounded context as well, because you also have to actually read back the actual liquid transfers that happens. So there's a lot in there than just creating a CSV file of the liquid transfers you just had. You have to upload, you have to download, so there's a lot in there. So I put that aside, and a nice little interface that you can actually talk to without having to know about robots. So if you have software that needs to talk to hardware, it's always a very good idea to put a boundary around it and to isolate the complexity of having to talk to your hardware, and not put that anywhere else. So then if you look at how you talk to hardware, right, there's understandability of that very specific problem in there, and it doesn't sort of fuzz everything else. So the other thing they had in common was that they want to measure whether or not something was successful. And ironically, we also call that quality control. Nothing with the quality control of warehouses. But we want to check if that works. And again, so basically what this workflow shows is that we sort of read everything of the DNA out of it, and we get a whole bunch of data, and then we have to analyze it. That's basically how it works. And if it can't give you all the sequence, then you know something wrong happened, right? That's turning it into a whole just didn't work, and that's why you can't read the DNA properly. And for that we have instruments. We don't call them robots, we call them instruments. They're not that big as robots, but we measure things on them. But having each workflow, also have their own instruments and also measure itself just is not very optimal. So what they actually did in the lab is that they created dedicated workflows that knew how to measure and knew how to measure very well. Right? It's again that I know how to do one thing and I want to improve on how to do that one thing. So that was a different department. And if it's, if the domain says that, hey, actually it's so specialized that we created our own workflow for it, and we give it to a very specific department that knows how everything works, then who am I to argue with that? So I don't put the quality control in my workflows. I actually have my workflows talk to quality control and say, hey, could you please give me the information on how well I actually performed? So, from the one to rule this all, we already have a few more boundaries here, which improves understanding the system. So if you want to look at your own code, say, okay, that's lovely, but I don't work in a biology domain. So then look at who are the domain experts? Like if you need a separate pair of domain experts to actually perform this very specific piece of business logic, then it's a good idea to isolate that and to create a model for that very specifically so that you can create understandability inside your software system. All right, and the last thing I want to look at of DNA and strain is time. Time is always a fun one in any given domain. But building small pieces of DNA takes 4 weeks. And building that large piece of DNA, it kind of takes 1 week. And I don't mean that we just build one single thing. We build about 300 or 400. But just doing that workflow once is 1 week, but doing the other workflow is 4 weeks. So that's quite a big of time difference. And because of that, quality control was used very differently in these two workflows. For DNA building, so imagine that on day 5, something fails. Now, if we look at strain building, the large pieces, it's not a problem. You know, 1 more day, and we can just start a new iteration of this workflow. And all I have to do is look at, you know, my data from the quality control and just re-add that large piece of DNA to the next week, and I want to build it again. And that's all I have to do. So very quick. But if something fails on day 5 in a 4-week workflow, well, that's not very handy, is it? So what they did is they used that quality control to redo certain steps to building small pieces of DNA. They looked, they said, oh, these failed. Actually, just for these pieces, I'm going to do everything again. And I'm going to keep doing that until I'm happy with how many have failed. Because, you know, nature, you will always have failures. You can't get around that. But I do want to limit this to 2 or 3. And that was a biologist's decision. They decided when to continue or not, whether or not enough had succeeded to continue. That was not something that the software could decide, basically. So, you know, we planned all those liquid transfers. We created work lists out of them. We sent them to the robot. But now what we have to do all of a sudden is that we have to change the plan, right? Because I have a plan for 4 weeks. And in that first week, things went wrong and I redid. So meaning that, there are things that failed here and I can't use those anymore. So my liquid transfers have officially become invalid and I need to create new ones. And I need to tell the robot to actually pick the one that succeeded instead of picking the one that failed. So I want to adapt my plan, something which I don't want to do for strain building. So I separated planning the DNA building workflow and executing it into 2 different boundaries. And then the thing is that, well, the plan has to talk to the liquid transfers. And it doesn't have to talk to the robots anymore because it doesn't execute, right? So it doesn't have to give the work lists. But my planning does have to talk to my execution, right? It creates the plan, it hands it over, it says, here is the plan I created, please execute this. And then at points where you have quality control, execution will actually real life adapt the plan so that the biologists can continue. And the logic behind this is that you sort of separate planning from execution from analysis, right? And quality control is also very much analysis, which is the second reason why I sort of wanted to extract it out of that giant workflow abstraction that we had in the beginning. And I'm pretty sure that if you look at your software systems, you will have something that sort of is more planning, and you have something that's actually really executing, and you have something that is analysis. And so you can create boundaries there, and you can create very dedicated models for those boundaries, because I don't need to understand how a plan was created in order to know how a plan needs to be executed. I just don't need to know those things. So I can forget about how I got the plan and I can just focus on how to execute it. And as a software developer, that makes it a lot easier for me as well. So What we had was one giant abstraction of workflow, which had about 10 of them, which completely ignored the domain, which were all the workflows that we actually had. But I started to redesign this according to bound context and problems that I saw that fit together. So we went from this. So like, don't get me wrong, this was very handy in order for a developer to look busy, because the thing was always on fire and you worked late because we were in Europe, and the people working in this workflow, like, they were very appreciated in the company. So from a job perspective and a pay perspective, maybe this is the way to go. But from an understandability perspective and your colleagues that also have to work in it, this is not the way to go. Right? We looked at two workflows. We looked at it very shallow. I touched on three very specific things that workflow have to do, which is robust liquid transfers and quality control. It is a lot more complicated than this, but already we have better models and a better understanding of everything that has to work. And as a developer, I can now actually gain extremely deep domain knowledge on this one specific thing, instead of having to understand all the workflows in that lab in order to be able to work with the abstraction that was in the code.
So maybe before we go on, do you have any specific questions about the workflows and the DNA building? Just making sure you're sort of on board with the whole. It's a lot, like the whole domain is a lot longer and more complex, of course, than what we can show.
Yeah, happy to talk about it. I'm here till Friday evening. If you want to talk bio, then come find me.
Yeah. So if you, sorry, there is a question.
I was just wondering how the workflow was implemented, if it could roll back. Was it a state machine or was it like linear, or how did it work?
It couldn't roll back. Like,
Right.
that was part of the problem, because they didn't understand all the workflows just on a very shallow level. And my workflow is the only thing that had to do those retries. So it was very much an exception, and that abstraction just could not do it.
Okay. But the new abstraction, how does that then roll back? Is it by making a new plan?
I'm not sure I understand your question.
No, so you still have a new abstraction where you have plans and executions
Execution.
of plans.
Yes.
So when quality control rejects that, what then happens? Do we make a new plan?
I think you're
Oh, sorry.
here with the execution. Yes, you mean, so how did I implement the retries?
Yeah.
So you just create indeed you create a new plan of a very specific piece, and then you sort of roll forward, and you tell your liquid transfers, okay, instead of going to this plate in this very specific well, please now go there.
So could one plan then turn into multiple plans if quality control fails?
That's not how they looked at it. It was very much one plan, with retries that needed to happen. So they didn't see it as, hey, we need to create a new plan. They really saw it as, during execution, we need to change that plan.
Okay, so does the new plan then have like part of the result embedded in it, and then the retries are the part of the plan that needs to be executed, or like how do we get the final result through when we have retried? And maybe this is too technical, but I have something similar where I work that's also hell.
Yeah, we can talk a bit more about it after
Yes.
the workflow, and then you can give me some specific details about your domain, and I can see if anything that I did can help you there. Is that okay? All right.
Anyone else? Okay. So these things are costly, right? We're telling you to find completely new abstractions. You have to do a lot of not just refactoring, but really remodeling, rethinking how the system works. Sometimes at the large scale, I was showing more of a, from the outside, like let's pull these systems apart. Gien was more at specifically these models for workflows. So it's all very costly, but these things have a compound effect, and that's probably one of the ways you can start convincing others in your organization to do this. Right? And by compound effect, it's the same as in finance, right? If you put a little money in an investment and you keep it there year after year, it will grow and grow. Well, maybe not in this economy, but it's the same with software, right? If you want something to still be around in 10 years or 20 years or longer, we'll have to start thinking that way, that we're not just building something to make it work, we'll have to build it in a way that we will still be able to use it and evolve it. We're still in sort of the stone age of software where we keep rebuilding everything every 10 years and then throwing it away again and rebuilding it again. That's not going to be possible forever, I think. Maybe with AI it will be different, who knows. But a metaphor that I think is useful here is understanding how we get there, right? It's gravity. The way gravity works is I write my first line of code, and then I write my second line of code probably below the first one, right, or close to it, and the next line close to the first two lines. The next function, the next object, the next whatever, it always gets attached to the thing that we have, and so the more stuff we add to it, the more it grows in mass, and the more it grows in mass, the more it attracts. It's always easier to add something to a system, no matter how badly structured or how bad the abstractions are. It's always easier to add something than to first break it down, separate it, and then add the thing, right? It's the physics of software, right? It's not just that we're bad programmers or anything, but at any point a new thing becomes, adding a new thing is a little bit more expensive than the previous thing you added, because your system is larger, has more mass, it's harder to understand, it's harder to figure out where it fits in. It's not necessarily designed to add that next capability or feature. And at the same time, the pressure is on because the whole environment around you, your project manager, your customers, whatever, expect it to be delivered as fast as the previous thing you delivered. So at any point, you're probably delivering slower because you have to put it somewhere in that mass. You get more pressure to deliver it faster or to catch up from the time lost from the previous thing. And at any point, the mass grows and it becomes very hard to separate it. Right? So that's like the mechanism, I think, the underlying mechanism of why we allow our systems to become like that. It's always harder to, easier to just add something, no matter how costly it becomes to add something and how slow it becomes. It's still faster than first separating the mass into smaller bits that fit and then find the right place to add something. But so it's also the opposite, right? You get the compound effect of this gravity, and you have to put energy into. Yeah, I'm going too far with the with the physics analogies now, and we already had a lot of biology. But that's the way I think about it. That's the way that I try to, at my clients, convince them or help the people I work with to convince their managers, etc. It's one of the many things, right? But it's advocacy for this idea, right? We have two forces competing. One is that it will become harder and harder to add anything to the system, and everything we add will make it more harder again. Or we have to start doing things now, pull things apart that seem low value because we didn't deliver any value, we didn't deliver any features, we didn't do anything new. No customer is happier, everything else is later. But if we keep doing these small improvements, we will be able to keep doing a lot of things over time in the long run. That was us. I was Mathias, this is Gien. Come talk to us if you want to know more about what we do with Artling, and have a great conference. Thanks for listening. You want to do more questions?
But there's already a microphone there. It's rude not to do questions.
I think.
No, does anyone have any questions? Because there's a nice person standing there with a microphone. There is a question there.
Okay.
Hi there. So just at the end, you talked about the kind of, not the trade-offs, but like massaging the message that you need to give to the business. What if you're having to deal with not with that conversation with engineers as well? So you're having not just an uphill battle with the business product side of things, but you're also needing to sell the message to your other colleagues as well.
Yes. Well, this is also a much longer question, of course. There are a few things that have helped me over the years. I studied some negotiation skills, and the main thing I learned from that is that everything is negotiable. The secret thing I learned from that is that people don't really like to negotiate. So if you negotiate, you're already a step ahead. This is dangerous knowledge. So if you approach these things as negotiation, and a negotiation is not bargaining, right? It's not fighting over who gets the biggest piece of the pie, but it's trying to really understand what people need, what even deeper than that, what value system they have, right? So maybe somebody is defending a certain position because they are in a value system of we need to deliver fast. Maybe they have good reasons, right? Why that is, because maybe they have knowledge you don't have. Maybe they know that the business is struggling, and if we don't deliver a lot fast now, then there's no business anymore to fix, right? That might be a valid reason. Or I've been in situations where I figured out that the company was actually trying to sell to a venture capitalist, look good on paper, sort of make sure that the numbers were right, and didn't really care about what happened after. Of course, that can be a bad thing, that can be a good thing, whatever. Right? But the underlying value systems, right? Maybe they've always been in environments where quality was not appreciated. Maybe now they are, but they come with the luggage, right? They come with the history of being in such environments. They're not. Maybe it's not been made clear to them that this environment does value quality. Right? It could be entirely different things, right? Maybe they are experts in something else. Maybe they're experts in performance and not necessarily in design and modeling and quality. Right? Maybe there's something there where you find common ground. In fact, I find that a well-abstracted, nicely organized system is much easier to optimize in terms of performance than a messy one. But that might not be how they may not even have had that experience, right? There's a lot of people who never have actually seen a large software system that was still understandable. If you've never seen it, you might not believe it's possible. And then, of course, if you don't believe that, anything you do is waste anyway, right? So there's all these things. There can be, good factors, bad factors. It can be things they will not tell you, or maybe they will tell you over drinks in a bar, but not at the office, right? There's many ways of trying to find what's really happening. If you just go, we engineers are bad at this, right? This sort of the social aspects, the social engineering, the negotiation, because we think this is the better way to do something. If I tell people, show them this is the better way, then they will all do it. That's also my hope coming here on stage, is showing better ways and hoping you will all do it. But it doesn't work that way, right? In reality, you have to find ways of balancing things. Value systems is a very good one. Understand, like, what heuristics do people have? How do they reason about something? Maybe they don't even realize that they make a decision because of these underlying heuristics. Right? Maybe they decide a certain way because of certain aspects they value. If you make those explicit, and I do this with clients, we actually put this on post-its and see why, like we have competing opinions about a decision, technical or otherwise. I find, okay, what sort of, why did you come to that conclusion or that decision or that opinion? We try to find those. What values do you have that underlie this? And now we can see all these values very clearly, and we can start looking at, like, do we think this is important? Yes, this is actually more important than this thing. Well, if we think this is more important than this thing, then maybe this is better decision. And it only works if you're open-minded enough to, see that sometimes the other person was actually right, given, the constraints and the values and the environment. So the very short version. But this is why we started as, very much on the side of software quality and design and modeling. And we moved into, with Artling, more into strategy as well, because great technical or design ideas for how the software should work, it doesn't matter if the politics and the organizational structure and the business vision and the product vision and all these things are not working well. So we sort of look at everything, do this sort of work, finding common ground, and then build on that again. Short version. Thanks. All right, I think we're out of time. Enjoy the conference. Have a great day.